Let x be the n-dimensional unit cube. Let k sub n be the series defined as the integral over this unit cube. What is the limit as n goes to infinity of this series? This comes from the Putnam Math Competition 1965, question B1. So the integral that we have to calculate is the limit as n goes to infinity of the n-dimensional integral of the cosine squared of pi over 2n multiplied by x1 plus all the way up to xn. We're going to make a trigonometric identity substitution here using cofunctions. The cosine of pi over 2 minus an angle theta is equal to the sine of the angle theta. To exploit this, first we observe the following substitution. We're going to let x sub n equal 1 minus y sub n, so that the summation of x1 plus x2 all the way up to xn can be expanded out as follows. In terms of y, we get 1 minus y1 plus 1 minus y2 all the way up to 1 minus yn. Collecting like terms, we get n minus the sum of y1 all the way up to yn. And this is equal to the sum of x1 all the way up to xn. And next, we're going to divide both sides of this equation by n, so that we get the sum of x sub n over n equal to 1 minus the sum of all the y's over n. Now with this, we're going to make a substitution into the cosine. So this is going to yield the substitution cosine pi over 2 x1 plus all the way up to x sub n over n is equal to cosine of pi over 2 minus pi over 2 of y sub 1 plus all the way up to y sub n over n. Now we take a look at the trigonometric identity of the cofunctions here, and we can make a substitution. We can let this equal the sine of pi over 2 y1 plus all the way up to y sub n over n. So the next thing that we observe is that if we take the integral that we're interested in calculating of the cosine squared of pi over 2 x sub 1 plus all the way up to x sub n over n, let's call this integral I1. Making an integral I2 with the sine squared as our integrand, we make the following observation, that since the cosine and sine squared are both equal to each other, we can also rewrite this I2 in terms of the variable x, since the y now became a dummy variable. So I1 and I2 are identical integrals, which allows us to write the following statement, that I1 plus I2 is equal to twice the integral that we're interested in calculating. We'll also exploit the Pythagorean identity that cosine squared plus sine squared equals 1, and that's what we'll get on our integrand when we sum these two integrals. So the n-dimensional integral from 0 to 1 of the sum of these two integrals, which gives us an integrand of the form cosine squared plus sine squared, is going to equal 2 times the integral we're interested in. And since cosine squared plus sine squared equals 1, we're integrating over an integrand of 1. And when we iterate this integration, we continually integrate over an integrand of 1. So that'll allow us to calculate that the left-hand side of this is always going to equal 1. So 2 times the integral that we're interested in is equal to 1, therefore the integral we're interested in is equal to 1/2. As the limit of n going to infinity, of course. I hope you enjoyed this integral from the Putnam Math Competition 1965 question B1. Please hit that like, subscribe, and notification bell for more videos.